Okay. So did you understand this part, driven dimers? Right. So somebody asks this question that, why cannot you treat the dimers as particles, single particles? Right. I mean, because in the correlation function, you can, if you put one dimer, if one site is occupied, then it is very likely that the neighboring site is also occupied. So there is a correlation between sites. So that is it's not directly single particle problem. Okay, so what is left to do? And I think one thing which I have not talked about is open boundary conditions. Non-periodic. There are two things. One is open boundary conditions. So that in that case, how do we use this cancellation scheme? This is one thing we should know. Second is, can you extend it to other things? Okay. So I will have. This is probably the last class. Not probably. This is the last class. So I will selectively go into things. Okay. So first, let us say that most important among them is open boundary, because that is the way the equilibrium systems that are inside. So you have a non-equilibrium system, and and you want to measure current, and it's an open system. Okay. So to measure the current, first thing is that you need also some conservation in between, because you see, if you have a pipe and water is flowing here, and you have some pressure here, you can define what can be the current. But let us say that you allow non-conservation in between, like you have holes in the pipe. So the current will be dictated by the holes, not by the boundaries. Okay. So by drive, if you want to see current, you rather keep the rest of the thing conserved. Okay. So here what we want to do, that you have a set of particles. So you have 1 and 0, and the simplest 1s and 0 in the lattice. And the simplest model is that 1, 0 going to 0, 1, which means the particles are drifted forward. And then you can say that particles enter here with rate alpha and exit at the last site with rate beta. Okay, so this is your particle model, and so generally the sites is I and I plus 1, I minus 1, and what else? And the length of the system is L. So now what will happen to the system? What is, so the main question is, one of the question is that what is current? So this is the problem which we wanted to solve, and we will see how it connects to the problem which we discussed yesterday during the tutorial. Okay. So what you have is that, so now if you want to write a matrix product answers, the probability of at each side, so I will denote it again, Si equal to, or Ni equal to 0 or 1. 0 means vacant, 1 means particles. Okay. And the corresponding matrices I represent E, and 1 correspond to D. Same notation. So what we have is that probability of Ni, this one has to be, D whatever, product of x of Si, Ni, x of Ni, product over I equal to 1 to L. So that tells you that if there is plus 1, then you write D, if it is 1, that is the 1. So x, that is the product over this. But then you cannot put a trace, because trace it makes it homogeneous, so you have to have a boundary conditions. There is some W and there is V. So along with this matrices ED, you will also have boundary matrices W and V, they need to be determined. W and V, those need to be determined along with this. So now let us look at the cancellation scheme. So your cancellation scheme, you are writing P is a P equal to some DE cross DE cross DE, like that. You are writing it like that, and direct product. And I was symbolically, I can write it A. A is basically this one, I am calling it A. Direct product I am not writing, but it is there. So why, and then the cancellation scheme is that so the P, along with this, you also have a matrix M, you have a dP by dt equal to MP, and M can be written as summation over I Ki, right? So Ki basically means that ith position you apply something. So M is summation over I, this is the way you are writing. Here also you have that same thing, you have L sides, every side something happens, and whatever happens here, the same thing happens here. Only thing is that there is an additional thing happening here at those two sides which you have to take care of. Okay? So earlier what you have is that M, like one cancellation scheme is that K, whatever matrix which is operating on 2 or 3 depending on how many sides. So K times A, right? So M times P equal to, symbolically, it will be like operating on these two, let us say two sides, operating on these two plus operating on A, operating on these two. Man, you know, there are many A's, I'm not writing all of them, plus A, like that, operating on these two. And that is the way on a ring it was cancels out. If you write A, this operation, whatever K times something operating on this is like K. This is K operator on these two. So this, if you write A tilde A minus A tilde. If you write it like that, it was cancelling out, because if you replace it here, A tilde A minus A tilde, that will, the second term will cancel with this, whatever left out here will cancel with this. Like that, in a periodic one, it cancels out. That was what you were doing, right? So what you have now is that along with this, you have vectors, which is W, and this side, I mean whole thing, of course, there is a lot of them, and there is a V. Okay? And the first term, let us look at this. So this will not be, this is not the whole thing. Along with this, you have also something else operating here, because particles enter here with rate alpha. What kind of matrix is that? It is not the same Ky. This one will switch or move particles with the same K, but there is something which will happen here. If this is vacant, you put particle there, right? So in the first side, you have an operation. What is the operation? If it is 0, then you make it 1 with rate alpha. This is at side 0. And what is the matrix which represents that? 2-dimensional or 4-dimensional? Like K is a 4-dimensional matrix, right? Because it is operating on two states, DE, DE. 4-dimensional. Do you know what is K is? Can you write K? K should come from these dynamics, right? 1, 0 goes to 0, 1. So you write it like this, na? 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, nothing happens. 1, 1, nothing happens. And 0, 1 is created from 1, 0. From 1, 0, 0, 1 can be created. Acha, sorry. Wait, sorry. What is my, I can use this? Okay, anyway, nobody is there to tell me what to use, what not. But anyway, so I'll use this. So this one is not, this is not the dimension. The way we have written is DE, DE, right? So I will write it 1, 1 first, and 1, 0, and 0, 1, 1, 1, 1, 0, 0, 1, 0, 0. Because if you multiply this, first you get DD, DE, ED, EE, right? E is your 0. So I have to write in this basis. 1, 1, 1, 0, 0, 1, 0, 0. So for 1, 1, the matrix has no elements, 0, 0, 0, 0, 0, 0 also no matrix elements. And 1, 0 loses with rate 1, 0. So the dynamics is 1, 0 going to 0, 1. So 1, 0 loses with rate 1. So 1 0 loses with rate 1, so this is minus 1 because it loses, and 1 0 cannot be created, so then nothing, right? So similarly 0 1, it can be created by from this 1 0, from 1 0 0 1 can be created, so this 1 0 0. So that's the matrix K, right? Okay, and KAA basically means that you can write the equations now. We'll write the equation. So this is the matrix K. But now along with this K1, K2, so your M, sorry, let me complete it. So your M will be K1 plus K2 like that, KL minus 1, right? And this last one, it's a different equation. KL minus 1 means last one. This one you can exchange, particle can go here. Here you cannot throw out particle, there is no zero, you don't have to check. This is single particle dynamics. The last one is plus some other matrix called HL. And this is from the beginning also M equal to some matrix H1. It is additional matrix because the one which will, if it is 0, in addition to whatever particle, if it is 1 it forward, but if it is 0 you also put particles here. And what is this matrix H1? H1 corresponds to this dynamic, 0 going to 1. Can you write the matrix now?
Here two sides are less, so I shouldn't be there with KL minus 2
KL?
So first left hand side, then this right hand side. So HR and HL in there. But then you are taking K to KL minus 1. Shouldn't it be KL minus 2? K sub L minus 2.
This is L minus 1. The last one is, so when you have AA, these two also operate and this side is L, right? And this is L minus 1. Anything operates on here, it is called L minus 1. I mean, if it is A, what do I call it? KL minus 1. L minus 1 operates on this and the next one, and L. That's the end. Before that also it is there, right? I mean, are you saying that before that there? I mean, plus KL minus 2 is also there. That's the previous one. KL minus 2 is this one.
I was asking that because on first side it is also open boundary. First L is equal to 1.
L equal to 1, it will operate because it is 1 0 can go to 0 0 1. Something it has to operate. If it is not 1 0 something else, anyway the matrix will not do anything. If that is 0 0, anyway it will not do. It is acting. It has to act. This matrix has to act there. Is clear? There is a matrix which moves particles. How many places you can move particles? Can move, if it is allowed. How many places you can move particles on a L site? L minus 1. First one you can move. Last one you cannot move because this is not it's a different dynamics. Just before the previous one you can move. If there is a particle, you allow. So that is fine. Is clear? Along with that, in addition, particle enters, so which is only operating on here. So let us write it. So the matrix is this one is here, this one, all these are there, plus H1 operating on A, right? So let us write it. H1 is a different color if I have one, not red. So the K is acting on red, H is H, and then H acting on A. This will act on H, will act on here. H1 will act on here. Plus there will be another term, plus the last one, particle goes out with rate beta. That's not same rate 1, it's a beta. So for that is HL. I mean, I will not write H1. This means that of act H1 here, 1 I'll write here, and HL, which means that AA, and all of the last one, there is a blue matrix, blue star matrix here. So I have to write these matrices, how it operates on A. I have to write it. I will figure it out. So what is the matrix first? 0 going to 1. So 1 0 1 0. How do you write it? What is the matrix? So 0 with rate alpha loses. So 0, 0, so 1, like first it is 1. 1 is gain from 0 with rate alpha. And 1 is gain alpha, it is 0 and nothing else. 0, 1 cannot be lost, and this is minus alpha, right? 0 is lost. This is alpha.
No, this 2 1 element will be minus alpha.
0? Huh, that's what I'm writing. 0 alpha, 0 minus alpha.
Minus alpha.
Why?
Because 0 is losing to 1.
But 0 is losing. Whoever losing, na? It is 0 is losing. Negative things comes, negative element comes in the diagonal. So 0, 0, 0, 1. So diagonals are negative, nowhere else. Doesn't matter what matrix you are writing. Always it is on the diagonal. Because whoever loses is the diagonal element in the matrix, right? The loss is always at the diagonal, because from that side wherever it goes, sum of column sum is written with a negative sign in the diagonal. So this is the one. Is correct? So this is H1, this matrix is H1. And what will be the other one? HL? So HL is 1 going to 0 with rate beta. So again I have 1, 0, 1, 0. 1 loses, so I will write minus beta. And 1 cannot be created, so 0. And 0 gains, which is plus beta. 0 gains with plus beta from 1. 0 gains from 1 with plus beta, and that is 0. So this is HL. Okay? So now my cancellation scheme, what will happen is that, look at this, what will this create? No, now let us write the cancellation scheme here. And so this matrix operating on, so basically 0, 0, 0, 0, 0, minus 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. This has to, it's a small, sorry, because you know how to do it, I'm just putting it here. So this is A, sorry, A means, now it is DD, 1, 0, DD, DE, ED, EE. So this has to be written as DD tilde, DD minus DD, this is DE minus DE, this is ED minus ED, this is EE minus EE, but then tildes. And tildes. Okay, that's the equation. So these are the equations generally you get. So what are the equations for from this? Let us write them clearly. So DD, which means from this side is 0, D commutes with D tilde equal to 0, and from the last one E tilde is E tilde, and from here you multiply, it will get 0. So this equal to E tilde, and from this, let us say this one is minus DE, what is that? This into that, so minus DE and plus ED, minus DE plus ED equal to DE minus DE. Huh? Okay, minus DE equal to that, and this is ED equal to E tilde D, E tilde D minus ED tilde. Okay, so this is the equation, and can you see a solution from here?
So that will be DE.
DE, right?
Not last one. It will be also DE.
That is DE. Okay. So dE, if I say that E tilde equal to 1 and D tilde is minus 1, then this will be dE equal to D plus E. So I take E tilde equal to 1, D tilde equal to minus 1. With this choice, dE equal to this is anyway satisfied, this is also satisfied because they are scalars, and this one and these two equations are same now. That only one equation I get, dE equal to D plus E from operation of this K is operating on this. But we are not sure at this stage that there is one part which is not cancelled. The boundaries you have to take care of. So what is left in the boundary that we have to take care? So what is left? So what is left is this part, and the beginning from here something is left, right? So let us write the first term. First term ka first term. Okay, so that is what will happen, A like that. And from here, when you operated this, right, so that will becomes equal to A equal to A tilde A minus A tilde times A. It's like this. So this one you replace by A tilde A minus A tilde, right? And these things, the second term onwards, that those has been cancelled. This one, A tilde, A, it will, from the next term, if you operate on this, it will cancel out. Let us write that if you want. Plus, in the second term, first is A, and then is A minus A, and then all A's. The second term. So basically this is again A tilde. So I'm just saying that let us call it tilde. So this term, A tilde and all A's, is same that A tilde, all A's. So this and that already cancels out. So this first term is left, A tilde, right? So if I say that this one is just A tilde, if I define H1 operating on A, whatever, this equal to A tilde minus A tilde, then this is okay, na? Then this will cancel out. Are you getting the point? What is left? So all these terms, this is there. There is the last one. We will take care of it. First thing is that from here, a term, this term which is left, A tilde A, all A's, right? So a term. So this is what is left over here is A tilde and all A's. And that has to be cancelled with this. So I just say that something H1 operating here, this blue thing, must be minus A tilde. Then it is okay. Then if it is minus A tilde all A plus A tilde all A cancels out. Right? So is it okay? If there is a doubt, ask it now. So this is the only thing which you want left out here, and that can be cancelled only when W, right? I mean there is a W also here, na? Everywhere there is a W anyway. Left side is W. So what you have is that H1 operating on W times A. So H1, right now, and H1 is a matrix. Let us write that. H1 is a matrix what? What is H1? 0 alpha, 0 minus alpha. 0 minus alpha, 0 alpha. This one has to operate on A, which means DE. Right? Must be same as minus of tilde of that. A tilde. Minus A tilde, which is D tilde, E tilde. And we have already chosen E tilde equal to 1. Otherwise, this simultaneously we have to solve. I mean, because I know that it will work. So E tilde equal to 1 equal to D tilde equal to minus 1. You can put this here. D tilde is? But there is a W also, na? Zero alpha, 0 minus alpha. Okay. Okay. So now what is that? Alpha times dW. Alpha times W times D. First equation. Alpha is a scalar. W times D has to be D tilde into, right, d tilde into d. So this is d tilde, W into d tilde, right? Huh? Minus. Huh? W is everywhere, there is a W. I mean, I saw everything is a W there is, right? When you are talking of a matrix product answers, you need a scalar. There is a W sitting everywhere. So this one is replaced by a tilde, but then W is anywhere there. So this is d tilde, but the W is there. I mean, otherwise there is no sense, right? I mean, you are no, yeah? Is it clear? So alpha WD equal to W d tilde. What do you want on the other side? Huh. No, but I will try to write the matrix. So that is beta. Can you write the second equation? Second equation is minus alpha WD equal to minus W E tilde. Huh? Okay, mistake, sorry. Now it is fine. This side is W minus W d tilde minus W e tilde. Great, it's fine. ठीक है ना? This multiply with this alpha E, not D. This multiply with this is WE. So these two equations are not different, but we'll see. Because this is d tilde, this is e tilde, we'll see that what happens. But let us go to the other equation, this beta. So beta will be what? What do you want for the beta? Last one. When it's the last one, here when you operate, this is already coming with a minus sign. So you want it plus. So what is the equation? You want this matrix minus beta, where? Minus beta 0, 0, beta 0 into DE and W, of course. I mean, there is a W here. WDE equal to, no, not W, V equal to, write it proper. Let's write it dV, EV, like that. This equal to d tilde V, E tilde V, and plus. So now what is the equation? Minus beta V, this I will erase. So this is minus beta V minus beta dV equal to d tilde V and plus beta dV equal to E tilde V. Now if you use E tilde equal to 1, D tilde equal to minus 1, E tilde equal to 1 and D tilde equal to minus 1, these two equations become same, one equation. D tilde, E tilde equal to 1. So dV, beta dV equal to V, that's what you get. So you have an equation here and you have beta dV equal to 1 V. That is one equation, and from here what do you get? Alpha W E equal to E. W. Yeah. Okay. So what does it mean? That you can take beta from this side. So it is 1 by beta. So let us write the equations again. Three equations which you get. So one is dE equal to D plus E and dV, D plus E, dV equal to 1 by beta V and WE equal to 1 by alpha E. W, sorry. कहाँ है मेरे दिमाग आज? Yeah, okay, sorry. So these are the equations. So what does it mean? Sum of two matrices is same as sum of these two matrices is same as their product, and one of the eigenvalue of D has to be 1 by beta, and one of the eigenvalue of E has to be 1 by alpha. Okay, so this is the one which we did earlier, right? I mean, yesterday these are the same equations we'd get in terms of A and E, and we have proven that there is no solution to it except when alpha plus beta equal to 1. Is it okay? The cancellation scheme is clear in open boundary condition. That is what I wanted to say. Okay? Is there anything further mistakes? Now it's correct. Okay. Okay. So now question that once if you do not know, like these things, right? It looks very simple, but there is no solution to this problem, except that there are infinite dimensional matrices. But some of the things can be calculated without doing much. Let us calculate first current, which is most interesting thing here. So the current, what is current in this problem? Current is produced when particle move forward, right? I mean, it's not when particle you drop there. It's current when particle moves forward, and particle moves forward with dE. So whenever there is 1, 0, wherever there is 1, 0, the probability that this particle will move is p dt. 1, 0 equal to 1 times dt. This is the rate at which, this is the probability at which particle with dt rate it will move. So that is just expectation, current is just expectation value of 1, 0, dE expectation value. Okay, so 1, 0 expectation value equal to current. That's what you want to know. So let us write that the partition function. Now partition function equal to d plus E whole to the power L trace. Is it very hot or I'm feeling like that? Okay. So d plus E whole to the power L, and there is no conservation here, so we are not bothering about how many particles are there. The system is free to choose as many particles as it wants. Okay. So d plus E to the power L. This was the partition function earlier. Now with the open boundary conditions, it will be W and D. Right? That's the partition function. This is the sum of all configurations, right? Because D, this is according to the matrix product thing, answers which you write, that probability of a configuration is W, all the ones replaced by D, all the zeros replaced by E, make a matrix product and operate with V. That is one configuration. If you sum all configurations, you call it the partition function, and that is Z. W this. So 1, 0 expectation value will be what? You write DE, first two sides. You can put it anywhere, first two sides, let us say, DE. But how is it possible that that you write it in the first side has to be same thing when you write it in the also any other sides, right? No, wait a minute. So what is your problem, physical problem? Here 1, 0 go to 0, 1, and particles enter with rate alpha, particle goes with rate beta. If the system has a current, the current is independent of same current flows everywhere, right? So if you put here and here, wherever you measure it should be same. Let us first measure at first two sides, like DE expectation value here, DE expectation value here, all the place we put D to the power DE. First we put DE, okay, from here. And let us see that if you put here and if you put here, you get the same answer. That is something which you want physically. So DE, and then what you write? T to the power L minus 2 WV divided by Z. Right? And Z is written here, WV dE to the power LV. Okay? But dE, you know what it is. dE is D plus E, which means T. So this is Z of, this is T, that is T to the power L minus 1 V. So ZL minus 1 by ZL. Simply. Right? So current that flows in the system is just the ratio of partition function of one shorter size divided by partition function of this system. Oh, wow, very nice. And that is the similar thing which you got in the two particle cases, ZL minus 1 by ZL. Okay? So this is somehow current is related to this. There is a meaning to it, but we will not discuss. We will go to further other problems. We will not discuss it here. Okay? So now question is that, do you see that if instead of here, if you put anywhere, it gets the same result, right? Because wherever you put, you replace it d by t, which means that d commutes with t. dE times d plus E equal to 0. Right? It commutes. Because dE is just d plus E. So it has to commute, okay? So that is the way you get this result. But question that if you calculate density profile, will it be same? Let us say density rho I. What is rho I? How do you calculate what is rho I? W 1 by Z, of course, and W. At ith place you have a D. If you want to calculate what is the probability, what is the density here, you just put a, what is the probability of finding a particle there. That's the meaning of density. Not finding a particle is 1 minus rho, finding a particle is rho at ith place. So ith place you put a D, and there are how many places here? I minus 1. T to the power I minus 1. Ith place you have D, and how much is left? T to the power L minus I times V. Right? Divided by Z. So you can calculate it if you know dE or something. So how, but now you, so for this calculation ZL minus 1 by ZL, you don't need the values, but you have to calculate it in terms of alpha and beta, right? Eventually everything has to be alpha, beta and L. So this has to be calculated. It is not that you have the result. You have to calculate it. Okay? But can you see that the density is different in different sites? Right? Because now there is a boundary. If I is 3 or I is 7, it matters. Because D is pushed to different places and you have to calculate it. So can you do this calculation? So the calculation is not, this is hard and I will not do it because this is not something. I will refer to your paper and you kind of follow this calculation. But let us calculate what is rho 1. One of them let us calculate. Can you calculate what is? But if you don't have a solution for D and D, then how will you calculate? I will write a solution for you then. So D equal to 1, 1, 1, 1, everything 1, and below also 1, 1. This is infinity matrix. So if you want to write it symbolically, this is summation over I plus I minus I plus 1, I plus 1. These elements are non-zero. This is a matrix, summation over all I, infinity. This is one matrix, this is D, and E equal to I minus plus I minus 1 I minus 1 I, summation over I. So this is diagonally all 1, just below the diagonal it is 1. You know what this matrix is? What is this matrix? Huh? I'm not asking the name of this matrix. Have you seen this matrix somewhere? You have not seen this matrix? What is the what is A? Huh? A or 1 plus A, identity you take out, the rest is just lower diagonal, that is A. This is 1 plus A, right? It will just raise the vector, lower the vector, and then you can have another matrix A dagger. So this is, one matrix is, I don't know what is convenient, let me check that. One matrix is 1 plus A. So basically what you are, so if you take D equal to 1 plus A dagger, I think I wrote it wrong, and E equal to 1 plus A, then you can see that DE equal to 1 plus A dagger into 1 plus A. So this equal to 1 plus A dagger times A, which is 1. I mean, because in the state space it is 1, and A plus A. So 1 plus A dagger is D, 1 plus A is E. So D equal to D plus E, and that is one representation. But with this representation, you have to know also what is alpha and beta. So what is W and V. So let me fix this for you. This is a long paper and all detailed calculations are there. So if you want to compute everything, I will go somewhere else. I think, yeah. A dagger is E, as I say that I wrote it wrong. 1 plus A dagger, because A dagger A you want. So this will be E, the D is the upper one. Okay. So DE I have written, and now W, with this I have to write also W. So W equal to up to a constant kappa, I can write W equal to kappa times 1 minus alpha by alpha, 1 minus alpha by alpha whole square, 1 minus alpha by alpha whole cube, like that. This is W, and V equal to, it's a column matrix, so 1 minus beta by beta, 1 minus beta by beta whole square, it goes on. So this is W, this is V, and DE just 1 plus A dagger. So this is, and kappa, it is just kappa, this is also with kappa, V is also with kappa. So I'm referring to you, there are representations, I will not be utilizing them here to calculate anything. So some alpha beta you can figure out. So WV can be figured out, you have representation, infinite dimensional representations. And the paper which I'm referring to is that, this is the first paper on this matrix product answers, a very nice one. So Derrida, of course, Derrida, and Evans, Martin Evans, and Hakim, I think. Hakim, H-A-K-I-M, Hakim, and Paskur, Q-U-I-E-R. Okay, this one, J physics A, 26, J physics A, 26, 1493, 1993. Okay, and this is what I'm talking about is equation 51, somewhere around equation 51. But he has many representations, right, 3-4 representations. So uniqueness of matrix product answers is not something which you know very well. So these matrix representations works. These are simple matrix representation which works. Okay. So now question is that, do you need, the question someone asks is that, if you don't know the infinity matrix, can you handle it? Of course you can, because so far when I asked that what is this matrix, you could not, many of you could not say, what is this matrix in quantum mechanics? You have been using it as symbol A and A dagger. It's not that you could not do a calculation in quantum mechanics without knowing the structure of the matrix. It's an infinity matrix. A and A dagger are, we don't need the representations in most cases. So this paper has also one chapter which deals with that how to calculate the observables without just getting them into the representation. Directly you can calculate the observables, okay? So these are kind of, calculations, and it will take a long time. I will not do it here, okay? But it can be done. Without representation, you can calculate the observables, okay? So now why this result is interesting? Let us tell the physical little bit of about why the problem is interesting, why you are working so hard into getting exact solution to this problem. Problem is that you have a line and particle center here and exit here with rate beta here, and here it is 1, 1, 0 going to 0, 1. That's the problem, right? So if you want to write a mean field kind of equation, if you write a mean field equation for this, so now you can think of, I'll erase all that. By the way, before going there, I wanted to calculate rho 1. Can you calculate rho 1? Rho 1 basically starts with d. So rho 1 equal to d t to the power L minus 1 Wv divided by W t to the power L minus 1 V, so t to the power L V. Can you calculate this? No, it is difficult because there is no equations which tells you this. But can you calculate E average? So 1 minus rho 1 you can calculate by putting E here, right? Because 1 minus rho 1 is like having a hole there. Having a hole, basically you should put a E here. But EW equal to just 1 by W, 1 by alpha. So this is just 1 by alpha, and t to the power L minus 1 is, this is just ZL minus 1 by ZL. So this is just J. Okay? Right? So I mean that has to, whatever current flows divided by this. With alpha rate particles flows in. So rho 1 minus rho 1 has to be this. So you can calculate also rho 1. So similarly you can calculate, right, some of the things you can calculate, like E square average you can calculate, DE you can calculate, and DE equal to, like, DE equal to D plus E, so that you can put and calculate, so like that. So some of the, rho 1, rho 2, simple things you can calculate, but arbitrary AI if you have to calculate, you need to know what is t to the power L minus 1, okay? And second one, before we go to the physical problem, other thing which we want is that when, okay, I think first I do this. What do you expect in this problem to happen? So what happens that, you can imagine, in a mean field way, you can imagine that there is a system site, and you can imagine that there are two other additional sites. This is 1, this is L, and this one is your it's an imaginary sites which you are putting it here. So you call it 0, and this one you call it L plus 1. And then you say that particle actually goes everywhere from 1, 0 going to 0, 1, right? From here, particles were entering with rate alpha. You don't say that. You say that as if this is a reservoir which always keeps the density here is alpha. Particle density here in this system is alpha. And then density is alpha, and particle goes here with rate 1. It's the same thing, right? If the density is alpha, finding the particle there is alpha. Probability of finding a particle at this site is alpha. If rate 1 would goes here, so effectively it is the same thing. So similarly, this site, the whole density, because if there is a particle here, it goes out, which means the whole here is maintained as density beta. So the particle density is 1 minus beta there. So as if this is just a reservoir, this reservoir is 1 minus beta, and this side is reservoir is alpha, right? Particle density here is alpha, particle density here is 1 minus beta. Is it clear? So what we are doing is that, or in other words, when you say the particle goes out with rate beta, you can also say that holes goes in with rate beta. So what is happening is that alpha rate, you are pushing particle into the system, beta rate, you are pushing hole into the system from the right, right? This is what is happening. Now, do you know what kind of situation this system will be equilibrium? Because now there are boundaries. The boundary density one is alpha and one is 1 minus beta. When do you think that this system will achieve equilibrium? Alpha equal to 1 minus beta. So which means that alpha plus beta equal to 1. And we have seen that when alpha plus beta equal to 1, you have a scalar solution. That is the meaning that you have a scalar solution when alpha plus beta equal to 1. So when is alpha and this is beta, so beta equal to 0 to 1, let me put, and alpha equal to 0 to 1, this is 1 to know, and alpha equal to beta, this line is equilibrium. Beta equal to 1 minus alpha. On this line, you have a scalar solution. Now what happens that if you have a drive here, if it is a diffusion, let us say that you, I don't know, maybe Abhishek has probably done that, 1, 0 goes to 0, 1. If you have particle move forward and move backward with the same rate, then you have a diffusion equation, right? I mean, you know that it is del rho by del t. If you go to the continuum limit, it will look like del rho by del t equal to del square rho by del x square. It is okay with you? Else I will calculate it. It's okay, right? But then if you have a PQ, goes forward with P, backward with Q, then P minus Q is like a drive, right? So plus additional thing, you get P minus Q, and here you get P plus Q, and this is P minus Q del rho by del x. This is like a mean field equation you get. And then what will happen is that if you go to continuum limit, this one scales, like, you know, if you have a drive and a diffusion, what is most important is the drive, right? I mean, this is kind of, when P is not equal to Q, this term is almost not there, because this goes to 0 in a lattice system, okay? Then what will happen is that this del rho by del t becomes del rho by del x, and so when P equal, first let us say when, what happens when P equal to Q. When P equal to Q, then del rho by del t equal to P plus Q, this part goes away, only the diffusion term which remains. If you want to go to a steady state of this system, then del rho by del t equal to 0, that's what you want. And then the steady state is del square rho by del x square equal to 0. And what kind of solutions you expect? What functions the double derivative is 0? Linear. So you have a linear function. So if it is diffusion, it's a linear function. And boundary conditions, so rho as a function of x has to be linear, ax plus b, like that. It's a linear function if it is p equal to q. And then there are boundary conditions. Boundary condition, left boundary has to be alpha. So this will be alpha plus beta, 1 minus beta into 1 minus beta into x by 1 minus beta minus alpha into x by L. So when x equal to 0, then it is alpha. When x equal to L, then you should have alpha alpha cancels, it is 1 minus beta. So this is the linear equation, which is alpha plus 1 minus beta times x by L. X means I by L. That is the density at different places. It's a linear density profile, like this side alpha, that side beta. Okay? So if it is P equal to Q, you just have a diffusion. So heuristically, if you don't have P not equal to Q, the most important term is this one. So this is ignorant. So this is first order differential equation, right? And the steady state, right, del rho by del x equal to 0, which means that it's a constant. But what constant? Which constant? So the density, because there is a first order difference, you cannot maintain two boundary conditions by putting del rho by del x equal to 0, and this side is that, that side is this. You just have first order differential equation and two boundary, it's overdetermined, right? So in these situations, what happens is that one of the boundary dominates, right? In these situations, one of the boundary dominates. So which one will dominate? So let us say alpha is much larger than 1, much larger than beta. Then which one will dominate? Which boundary will dominate? The alpha side boundary, because alpha is very large. Okay? So when alpha is very large, then the left boundary will dominate. And then what is the density of the system? Alpha, because the left boundary density is alpha. So what the profile, if alpha much greater than beta, the profile of the system from the left, it will remain alpha, it will go like that, constant. And in the other boundary, I mean x equal to 1, x equal to 0, x equal to I by L. So on the other boundary, it has to go and match wherever beta. If beta is here, it will be here, 1 minus beta. This is 1 minus beta. Or beta is 1 minus beta is here, the profile look like that. but it's only like a boundary layer here. But here up to this, all through the bulk, it will be alpha. Okay? And when alpha is large, so the density is very, very large. So that is one phase. So this density is called high density phase. The profiles look like this. And there will be another one, low density phase, when beta is greater than alpha. Then when beta is greater than alpha, the particle density is 1 minus beta. But this beta is still dominant because it's very large. So the whole density will be the 1. So the boundaries look like beta, some here. And this side, depending on which way alpha is, this is beta, and it will look like that. So these are low density phase. What will happen if both alpha beta is very large? Very large, I don't know what is very large. That has to be decided by the exact solution or something. So alpha is much greater than something, much larger, alpha beta large. In this situation, what happens is that from the left hand side, particles are fed into the system. From the right hand side, holes are fed into the system. Right? I mean, so now the density, the system cannot decide what exactly. The density will remain half. That's the maximal density which you have. So the density here will be half. So the profiles, this is called, I'll call it MC phase. I'll tell you what is MC. So what will happen is that the bulk density will remain half. This is half. Okay, and this is again 0 and 1 and x, 0, 1, x. So now it depending on whether this way, it can be any of them. Depending on where alpha and 1 minus beta are, the profile look like one of them. In the bulk, it is always half. But now in any situation, doesn't matter what will be the current in the system? Mean field current. Huh? P minus Q, rho into 1 minus rho, but P minus Q is not there, Q is 0, P is 1. So rho into 1 minus rho, right? So the current is always rho into 1 minus rho. So when it is half, so the current J equal to rho into 1 minus rho, J is a function of rho, and how does rho into 1 minus rho look like? It looks like that, right? And what is the maximum current? At density equal to half, and the current is 1/4. So here the density rho equal to half, and the density is anyway 1/4, rho into 1 minus rho, always, in all cases. Here the density rho equal to alpha, here rho equal to 1 minus beta, low density, like this, okay? So this one, because this even rho equal to half, the current has a maximum. This is called a maximal current state. So actually, everything I could not prove, but I'm just saying that the point is half. That this is the phase diagram of the system. So what you have is, this is a density, this is half, and this is the phase. So this phase is maximal current, and this is not anything. This is just kind of a line where equilibrium is. You should know that there is a special line, but the phase transition line is this. Okay, so this one is high alpha, is this side. This is high density. This is low density. This is maximal current. Okay, so all through this region, the density is half. Here, density, low density. So density rho equal to 1 minus beta. Here the density rho equal to alpha. And everywhere J equal to rho into 1 minus rho in the thermodynamic limit. There are corrections to this formula, but all these can be calculated exactly using this. So which means that the partition function has different limits, different asymptotic behavior in different zones. In this zone, so now this is also like, this was there. This is not a transition, but this is there. Some line is there. So this zone, this zone, this zone, this zone, and this zone. The partition function will have different asymptotic behavior. Okay? This is just information. One more thing I wanted to say on this problem.
What is difference between lower two nodes? So like you have written that here it's high density. No, these two.
These two.
These two.
These two.
Yeah.
Uh-huh.
In both there is high density.
Both are high density. Phase wise there is no difference, but the profile will have a difference. So you see, when it is here, the density is alpha, but if it is here, then in this zone alpha is greater than beta. So then the profile alpha is greater than beta. No, let us look at this one. Below in this zone, alpha, this is a line which alpha plus beta equal to 1. This zone is alpha plus beta is less than 1. So alpha is less than 1 minus beta. Alpha plus beta less than 1 in this zone. It is high density, I am talking of this, and this is a line, this was there. This is the region, in this region, alpha plus beta is less than 1. So which is alpha less than 1 minus beta, right? Or 1 minus beta is greater than alpha, right? So now, this is alpha, 1 minus beta is greater than alpha, that's what you get. 1 minus beta is greater than alpha. So this is the profile in this zone. And in this zone, the profile looks like that. That's a physical macroscopic difference. But these are boundary layers. I mean, if you rescale your system size to 0 to 1, this will eventually disappear. For larger systems, it will go like that. Even larger, it will go like that. Eventually, everywhere it is a constant. That's what you will see. Okay, one more thing I wanted to say as a statement. Let us say that alpha beta is very large. Okay, so I'll just look at these equations. Here, 31. No, these were 52. Alpha equal to beta, much greater than half. But it can be alpha beta, any both of them, both alpha beta greater than half. Okay. So if when alpha beta greater than half, there are zones alpha beta much larger than half, both alpha beta greater than half. The partition function, which is w t to the power L v, this one behaves as up to a constant. I will not write the constant, it's there, equation 51. I am just quoting it. This is 4 to the power n L divided by L to the power 3 by 2. Okay. There are other regimes, there are different things. Somewhere it is 1 by square root of L, but this is the maximum power you can get, 3 by 2. And that regime is here. Some other places it is 1 by n, 1 by L. Some other places it is square root of L. But the asymptotic form in this zone can be calculated exactly, which is being calculated, follow the calculation, it is this. Okay. So now, current, if you want to calculate current, is just ZL minus 1 by ZL. Just wanted to calculate J of L is ZL minus 1 by ZL. What is that? This is 4 to the power L minus 1 by 4 to the power L, which is 4. I mean, we don't care about. L to the power 3 by 2. So 1 by ZL is just L to the power 3 by 2 divided by L minus 1 to the power 3 by 2. Right? I mean, other constants, it doesn't matter. Is it clear? So now what is this? So this is 1 divided by 1 minus L inverse whole to the power 3 by 2. So this equal to 1 plus by 1 by 4 is also there. Let us say, why should you drop that? 4 to the power L minus 1, 4 to the power L, that is a 1 by 4. So there is a 1 by 4 into 1 plus 3 by 2, na? L to the power minus 3 by 2 by L. 1 plus 3 by 2 by L. Plus other terms. Okay, so the first correction is 3 by 2 L. I just wanted to, I will use it somewhere. So that this current, you use it somewhere. Okay, we'll stop here and go to the next problem and use this expression somewhere. So if you have questions, you can ask me here. So we actually discussed, no questions? That is L goes to infinity. This is from mean field I'm just talking about. That's the exact calculation with corrections. If you want higher order corrections also I can calculate, because this is the exact expression. And yeah, asymptotic form is also known. Full thing you can calculate. This is from the infinite dimensional representation. You can use the infinite dimensional representation to calculate it explicitly. But the functions are pretty complicated. It's like p factorial 2 p minus 1 factorial into 3 to the power 5, like that. It is a very complicated expression, so I don't want to. Alpha beta very large. Because once alpha beta is very large, you go to that zone. The actual value of alpha beta, of course there is an expression there, but it doesn't matter much, because that goes down, right? The ratio these are constants. JL by JL minus 1, it will go down. Whatever alpha beta, it cancels out. Khali L changes. And I'm looking as a function of L. JL is a function of L. So that is a constant. L goes to infinity. There is a fixed current flow, 1/4 maximal current flow in the system. That is the reason I wanted to keep 1/4 also there. So when L goes to infinity, you want alpha beta very large in this zone, the shaded zone. In the shaded zone, the current has to be 1/4, and that is the 1/4 which is coming from there. Okay. I don't know. Okay. So there are two things which I can do. One, keeping the time in mind. One is that yesterday during the tutorial, you solved this problem. You started and you solved. You everybody took part in this. Getting into the problem that. So I will use this part of the board, I will erase and we will use. So those which were not there in the tutorial, just be patient and ask other people how it was that. Yeah. So the point is that there is a model. You just say that A0 going to 0A, it was PQ, but we just say that this is alpha, this is 0A. So A particle just move forward with 0A, B particle goes backward. That is also that alpha. Okay, alpha, and then another one is AB going to BA. These are the three things only. So what does it say? That A very quickly passes 0 and goes this way. B, wherever B is, they are coming this way. There are A's coming this way, and then when AB comes, they meet and exchange. So what is a good situation if you have a lot of particles? That the dynamics will go into all B's. If you have all B's, all A's, let us say, if you have all B's, all A's, and all zeros, a situation like that will not move much, because B, A, it is BA, nothing will work here, no dynamics. AA anyway no dynamics, 0, 0 no dynamics, A0, here once a while particle goes away, but then it will come here, it is AB, and B once a while come to the other side, very little. So once you get a situation, it's a large block of A and B separated, they will remain probably separated. With this idea, people looked for phase separation transition here, and if you simulate it numerically, you will find it. So this was the problem which I was talking about. This one will give you numerics, it will give you a phase separation transition. And yesterday, people have figured out that the relation between AB, if you take O equal to VW, if you take O equal to VW, and with some choices of tildes, because A tilde, O tilde, B tilde, with some choices of O, B tilde, you find A plus B equal to AB. Okay? And then AO equal to 1 by alpha O, A something like that, AO, I mean, if you call it DE, this is the same equation you saw, only that here you get beta, alpha, here you have both of them are alpha, PQ or something. So this problem, the matrices will satisfy these equations if you identify D equal to A, E equal to B, and WB equal to O. Those which are there, they have only done the problem. So what is means, right? You write the equations if you are confused about this, or if you are not there, then write the equation for this model, matrix equations. It's a scalar choice of O tilde, A tilde and B tilde. You can reduce these equations to DE equal to D plus E, alpha DV equal to this, alpha WE equal to W. These are the equations we have seen it at a time, and this is the same equation. So what does it mean in this model is that if you have a lot of like this, so every time you have a O means 0, so the zeros are replaced by W, VW. So zeros are replaced by VW. So 0, A, B, A, B, A, B, and 0. So this will be 0 will be this, AB will remain as a matrices, and then there will be another one which is VW. And once you have this becomes a scalar. Okay. So what happens is that between any two consecutive zeros, there are some number of particles, and this is a block because zeros are right. When you close your eyes, or zeros are no vacancies, right? There is nothing there. It's still A and B particle. So you have some section of particles, you call it a block, and then there is another block, then is another block, there is another block of particles. And these blocks are independent, right? So now question is that, but the blocks are independent, but sometimes this B can go to the other side. So thereby, it will decrease the size of this block, increase the size of that block. These particles can move. So the rate at which the particle move is same thing as the current which is passing through this block. Is it clear? Because who moves the particle? The current. And current of what? A or B? A and B are the same because it's only opposite in the sign. Whenever A goes forward, B also goes backward. AB goes to BA, right? That is the way the current is generated. So the current of A is same as current of B. We are only talking of magnitude, they're same. It's only directions are different. And the current, this is a problem which is a TASAP problem with rate alpha and alpha. So if alpha is very large, the current which is flow through this system is same thing as what I write it here. So the current which is flowing through this block is exactly this, whatever JL is ZL minus 1 by ZL. If the size of the block is K, then Jk goes as 1 by 1/4 into 1 plus 3 by 2 by L. Okay? This is the current. Now I'll stop there. And I just wanted to make one more statement that why this situation will never occur, a proof. The next statement is this one, that we also know in the previous class we defined another problem. The problem is just this. There is a particle, there are boxes, and there are particles, and particles grow from here to here with rate u of n, if n is the number of particles here. And in this case, we can ask, so the steady state of this problem is known. So probability of having first box as n1 particle, second box n2, third box n3, and lth box nl. This one is equal to some function of f of n1, f of n2, f of n3, like that, f of nl, up to a conservation law. This is the thing. It's a product measure, solvable exactly. With fn, f of function n can be written directly as product over I, which I'm not proving. It's known. I equal to 1 to 1 to n, or 1 to n, 1 by u of I. So if you give me what is the rate, what rate, if it is 1 particle at what rate it goes, 2 particle what rate it goes, 3 particle what rate it goes, I'll put it here, find this function, put it here, find the full probability. That's the formula. Along with this, also there is a statement, these are all can be proven, not very difficult. Half an hour it will take me to do this, but I don't have that kind of time. So if you think some of are interested, you want to do it, you can do this, okay? So the statement is that if u, so the statement is if un, it can be solved for any n. If un, you can expand in the asymptotic form, like large n, how does un behaves? So if un expand it large n, then it will be u infinity, about u infinity into some 1 plus something divided by n plus something, if it is a good function, something divided by n square. It's an analytic function, then it will behave like that. So this plus this by n plus this by n square, something like, so that n goes to infinity, it is just u infinity. Okay? So any function, if you expand it like that, the demand is that it is only the residue part, whatever is coming here, that I call it b, and this one some other number. This is the one which dictates whether the system will have a phase separation transition or a condensation. So the demand is that if you expand it like that, b greater than 2, you have a condensation transitions. Condensation basically means that there are particles which are throwing particles to the next box like that. Eventually in the steady state, you will have some box with huge number of particles. Okay, that's what it is. Now, look at this problem. So you have this 0, and there are A, B, some B, A, B, and then A, B, 0, 0, A, B, something like that. And then you have a box here. So if you identify zeros as boxes, that the particles, you don't bother about whether it is A kind of particle, B kind of particle, because when they go out with the same rate alpha, and the current is just Jk. The current is Jk. So this Jk is same thing as Uk. The rate at which particle moves out from here, this box, is Uk. Right? I mean, all I'm saying that 0 is like a box, you just invert it like that. So there are particles which are in the column, this box with 2 particles, this box with no particle, this box with 2 particles, so box with some particle. And the rate at which particle moves from here to here is a current, and current, you can call it just the UK. Right? So if you want to consider this problem, firstly, the boxes are independent. Of course, the boxes are independent here. You have proven this because this W, wherever you put this one, you are putting a vector like that, it making it independent. So the boxes are independent, which is also factorized here, exact. And the rate is same thing as Jk, and Jk we know explicitly that it is 1 plus 3 by 2 by L. So which means this B, if you write it as a rate B is 3 by 2. So that according to the demand, B greater than 2 only, you can have a condensation transition, right? And here you explicitly show that B equal to 3 by 2, so you cannot have a condensation transition. Okay? So a very nice exact calculations can be done in few minutes, like half an hour, just to prove why B greater than 2 gives you a condensation transitions, which I am not going to do. Okay, so this, if there is a if some people still survive and want to stay back and in some times during the tutorial or something, then we can do this. Otherwise, we will drop this. Okay, so that is the reason why this ABC model, this model will not have transition. Then people come up like Lebowitz, Katz, Spoon, of course. Among these three, 2 of them are Boltzmann. I think Katz also gotten, I don't know. So they have come up with a model that what should you do to this model so that you can have a phase transition. What you do, modification, is that AB goes to BA. you can think of this plus minus goes to minus plus. Same thing, you're just naming it. But you say that xy, xy. It depends, the rate depends on Ising-like rates. You put Ising-like rates there. So, which means that this plus minus particle has some interaction. Okay? Once you do that, you can have a phase transition just by making B greater than 2. Okay? So there are a lot of many articles in this one. I will cite some of them so that if anybody interested can read it more. One of the article, okay. I'll erase this now, it's not needed. So one of the article is this KLS model is Kafri, Mukamel, Kafri, Levin, Mukamel, Torok. This is PRL 89 035702 2002. Okay, so this one talks about criteria of phase transition, the one which I say that this kind of models can be mapped into this process called zero range process with B equal to 3/2, and there is no phase transition here. So this is the physical review letters. And also soon after we have also some work on this, Evans, Levin, PK, Mukamel, and yeah, that much. EPJB, oh, I should remember. EPJB 41 223 2004. So this is more of a review kind of article on this, and more things like, you know, density and things like that. Okay, so the matrix product answers, I think I have given the reference, like the best one, Derrida. Of course, all the calculations are there for the infinity matrices. But there is a matrix product answers review. It doesn't talk about the simple matrix thing which I'm talking about. It doesn't talk about direct product. It also talks about mostly this particular problem, tasse upon a ring, tasse upon a open boundary. And the title of the paper, because that will interest you, I suppose, the title is Matrix Product Answers, a Solver's Guide. Okay, so that is by John, that is Martin Evans, Blythe, I think, which in Warsaw or something, is, I don't know now where is it, and Evans, and this is Journal of Physics A, okay, and 26, sorry, Journal of Physics A, 40, देख के लिखना मुझे बहुत मुश्किल होता, R333, 2007. Okay, this is matrix product answers in a solver's guide. And there is another one, right, you know, I don't know, I mean, you know, maybe I don't want to advertise this. So a lot of matrix product stuff in terms of this many particle without hardcore interaction and things is one of my students' thesis, Amit Chatterjee. So you can look for that, but I'm not advertising that, you know, you just look for this. If you want to read this also, that is also a good source of reference. Other thing is that this says some typos, that's the reason I'm not sending you. I'll fix the typos and give you this set of problems, like, so here I have some 5 problems, including, you know, some results are quoted, like the one which I solved. So the problems are not like, find out what is the current in driven dimers, then you are clueless. But if I say that, so that the current in the driven dimer is 1 minus rho by this minus this by that, then you know what to look for, right? So the problems are set that way, stepwise, like first you calculate density, next you calculate this. I have writing, yeah, too much. So this is a short way I can actually work out the problem without truly working it out. So this is this notes, I will share it with you also, okay? And in case, if you have problems, like, you know, somewhere you are interested in some matrix product answers or some other problem, non-equilibrium steady state, and you think somewhere I can be of any help, just drop me a mail. We can fix a time and discuss, okay? Matrix product answers or any other problem related to things. So I'll also put my, this is not an advertisement, but hope it will help. IISER, I don't know how to write, rcol.ac.in. Okay? Yeah. Email I'm more comfortable, otherwise I could give also the mobile number, because then you don't get. My mobile is permanently silent, so I mean, it never rings, so I don't have a. Okay, so I think I stop here. There was something which I wanted to do in, acha, one more thing. It's really 5 minutes, I will take care of that. So question is that instead of doing this matrix product answers for systems which look like that, why not? It's not very difficult. No. How many of you know what is a zero range process? You have a solution of zero range process you've done. Anybody who has done solution of zero range process? Because the same author, Martin Evans, they have also a zero range process review on solution of zero range process. That's a very nice review. I suggest that you read that. And it's a very simple problem, like particles just moving forward and backward. One dimension, you can have a phase transitions, you can have a lot of interesting stuff. Analytically, you can calculate, and it will be very satisfying, reading that kind of articles and solving some problems on that. Okay, very nice, satisfying. Okay, useful, I don't know. That is it's a different question. Okay, so I will not do this, because if you have not appreciated this, or if you have not seen it earlier, you will not get the charm of how you write this into matrix product answer. Don't forget it. Just particles moving on a lattice is good enough. Okay. Let us do other thing. How to do matrix product answers in 2 dimensions. Okay. And what are the just 2 minutes? I will just use this, because I will tell you what is the difficulty in 2 dimensions. What is the difficulty in 2 dimensions? Is that, so if you have 1 0 1 1 0 something, or plus minus, you can write it D, D, E, D, E, D, D, E, D, and without saying anything, this becomes directly an operation in matrix, because you just, as if they are multiplying. And just by multiplying, you can get a matrix. Matrix written one after another can be treated as a product, and that operation is valid. And that operation can be taken further, putting trace and putting vectors, and a lot of things you can do. Now in 2 dimensions, you will have a situation where you have 1 1 1 0 0 0 1 0 1 1 1 1 0 1 0 1, like that. So this situation will convert D D D E D E D E D D D D E D E D. This is what you do, because each side you have a matrix. That's what you want. That is the way you do. So if you want to find what is the expectation value of here having a particle, just put it D here, everywhere D plus E. That is the way. But question is, what is the operation? What is that operation which can take a square of such things, matrices, and give you a matrix of the same dimension, or make a trace or an algebra out of it? Okay? There is nothing. I don't know what to do. And you can write that, okay, this is itself is a bigger matrix. True. But in that matrix, in the 2 dimension, like, so if you were moving forward, a right neighbor is different, far away, right? Here in 2 dimension, here you go here, and then there is a left neighbor, and this one is yourself. Quickly you come back. There is a loop. So the information in a 2 dimension, somebody was saying, maybe you can call it topology. That this to that to this to that is here only. And that kind of information is not there in matrix. So you do not know this to that to this to that is E. You don't have such information. So an operation like this is invalid. So you don't know even to start with how to define a matrix product answers in this situation. What I did is this, and it works. So every such thing can be written as, this is just, let us call it 1, and I'll just give you the idea and I will not do it. One problem, at least I could solve it using this, very nice, 1 0 1 0 1 1. Let us say this, 1 1 1 0 0 0 1 0 1, something like that. So every two-dimensional thing composed of, actually 4 by 3 हो गया, that's ठीक है, कोई बात नहीं. So it is like that, a line, one like that, 3 red lines, and 4, 1 2 3 4. There are 4 yellow lines. A square is composed of, in this square is composed of 3 red lines and 4 yellow lines. So when you go through the red lines, you count E, D, and let us this one, you red lines. First red line is E, D, E, D. Second red line, and then I put a trace. Each line, because it's periodic boundary condition this way and that way, I put a trace. Second red line, I will put trace of D, D, E, E, times trace of E, D, E, D, 3. And now I will go the other way. Trace of, times trace of E, D, E, times trace of D, 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 times trace of E, 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 times trace of this. This will work with a sum cancellation scheme. I will not tell you the details, but this will give you the, it's a very nice algebra, and you can actually, if the dynamics is asymmetric in x and y direction, you can use D, when you go through this, you can use D perpendicular. When you go through this, you can call it D parallel, okay? And still it will work. It's only to write, how to write D plus E whole to the power, how to find partition function from this. From Ising, at least for simplest one like Ising model, you can work it out very clearly, it will work. And this DE is no different from the DE which is solved in the Ising model. For Ising model, two-dimensional Ising model, this way can be written using D equal to e to the power beta, e to the power minus beta 0 0, E equal to 0, e to the power minus beta, 0, e to the power beta. If you use this E for every configuration and try to write a trace like that, you get the Ising weight, e to the power minus beta, Si, Sj, everything you get it correct. You can check it, it's not very difficult. Okay? So it is, so the way what I wanted to claim is that a two-dimensional matrix can be constructed from a knowing the transfer matrix in one dimension. That's the same matrix which works. If you know the transfer matrix one dimension, the same dynamics x direction, y direction, if you put, it will work. Okay? So the matrix product answer, so this is not useful. This is just rewriting the known steady state in a two-dimensional square lattice in matrix product form. I'm not saying more. In an unknown problem, you can still use it with certain cancellation schemes. You can make it work. This has not been published because a full solution is still little far away, and I was not very happy. So I have a problem where in 2 dimension 1 1 0 going to 1 0 1. What does it mean? That if it is 1 1, if there is a particle here, it will just move here. Or it is 1 1, it is a particle, it is a vacancy here, it will move here. But isolated particle do not move. So that will exhibit a phase transition, observing state phase transition that one can show, and I could calculate beta in that case equal to 3, which is very strange. E beta means critical exponent, one of the critical exponent can be analytically can be calculated, and we could get beta equal to 3. But somehow I was not very happy with the solution because it is, I don't want that in the calculations, little bit approximation somewhere, I could not make it out. So it's still there lying, but yeah. But this is the way to do it, matrix product in 2 dimensions. Okay? I think I stop here. Wish you all the best. And if you have any issue or any problem in matrix product answer or something, drop me an email and we can talk further. Okay? And if you, I don't know who to ask. I will be here after 4:30. So if you are still here and if you want to continue, we'll continue, otherwise we'll go. Okay? If in case you have questions. I stop here. Bye. Yeah, bye-bye. Thanks. I'm here next week, but then you don't have time.